We remember, hopefully, that there was a limit law for quotients. It said if you are trying to calculate the limit of a quotient of two functions, that you could separate the numerator and the denominator and apply the limit to each separately, and then it would be fine. So it's tempting to think that that would carry over to calculating derivatives because derivatives involve limits. But just like with the product rule, that doesn't transfer the way that you want it to. If we're taking the derivative of a quotient, f divided by g, it is not the same thing as putting the derivative of f in the numerator and the derivative of g in the denominator. So if that's not the quotient rule, what is? Well, we can go through the exact same derivation that we did with the product rule, except for we start with j being a quotient of f and g rather than a product. So we set up j prime using the limit definition for the derivative. We replace our definition with what j is equal to, that's the f divided by g. I'm not going to go through each of those steps because it's so similar to the product rule. I think you could probably do it on your own. But I will give you the punchline, which is that if we're taking the derivative of a quotient like j, quotient rule basically looks just like the product rule in the numerator. And then the denominator is that original g function squared. And I've written it in a second notation. So we have the prime notation for the quotient rule, and then we have the kind of fraction notation for the quotient rule. But they both say the same thing. They say if you're taking the derivative of a quotient, you're going to take the derivative of your numerator, and you're going to multiply it to the function from the denominator. That's multiplying times g. And then it says you're going to take the derivative of the denominator and you'll multiply that to the numerator. So take the derivative of g and multiply it times f. So we are taking the derivative of each function separately, but notice that we have to multiply by these special factors to make this work. And then, even more importantly, we have to divide by g of x after we've squared it to follow this pattern. Let's try a couple of examples and see if that works out. So we have this function k. K is a rational function. The numerator of that rational function is 5x squared. The denominator is 4x times 3. So that would mean that our f of x is 5x squared. Our g of x is 4x plus 3. That means f prime would be 10x, just using our power rule there. And g prime would be 4. The derivative of 4x would just be 4. The derivative of 3 is 0. So g prime is equal to 4. When we go to calculate k prime, we're going to use that pattern that says f prime times g minus, that's a little bit different than the product rule. We have a subtraction here, minus f times g prime. And then once we have the numerator written out, we will divide by g squared. So to calculate k prime, let's plug in everything we have. F prime looks like 5x squared times g, we need that in parentheses, 4x plus 3, minus the f function, which is 5x squared. Oops, I wrote that down wrong. Start over. For k prime, we need the derivative of f, which is 10x, times g, which we need parentheses for, minus the original f, which is 5x squared, times g prime, which is 4. That's our numerator. The denominator would be over the original g function after we've squared it. And so technically what we have on the screen is correct, but we've taken all these years of algebra, so why not use our algebra skills to simplify this as much as possible and multiply any constants together, combine like terms, whatever we can handle here. So in our numerator, we'll have 40x squared plus 30x minus 20x squared. And then in the denominator, leave that factored. You don't have to multiply out the denominator. Almost every application that I can think of would prefer for you to have everything completely factored. So let's leave the denominator factored. Save us some time. I do notice in the numerator we have like terms, so let's go ahead and combine those. 40x squared and negative 20x squared, that looks like positive 20x squared. And then we have 30x, and that's over our denominator of 4x plus 3 quantity squared. So finding the derivative of this function k, which had a quotient as part of its definition, required us to use the quotient rule, and our final answer was 20x squared plus 30x divided by 4x plus 3 squared. Let's try another one of these. So different function k, still a quotient though. Our numerator I'm going to call f of x, looks like 3x plus 1. Denominator I'll call g of x, that looks like 4x minus 3. And we're going to use our quotient rule, which needs to have f prime. The derivative of f would be 3. That needs g prime. The derivative of g would be 4. So now when we go to do k prime, we will have f prime times g of x minus f, the original f, times g prime. And then all of that is divided by the original g, the OG squared. And then of course we would want to try and clean that up. So we will distribute. Be careful distributing on this second term in the numerator. Not only is there a minus, but there's a 4. So when I calculate that, I'm going to think about multiplying 3x times negative 4 and multiply 1 by negative 4. And again, we'll leave our denominator factored. In the numerator, I have a 12x and a negative 12x. Those guys cancel each other out. Then we have a minus 9 and a minus 4x. Those don't get any nicer, but I will rewrite this so that it looks a little better. And that would be our final answer for k prime. So here are the differentiation rules. Now that we have them, we will not go to the limit definition of a derivative first thing. Instead, we're going to try to use these rules, and then we'll save that limit definition of a derivative for cases that these rules don't apply. So quickly, let's review the names of them. This first rule is the derivative of a constant. That's always equal to 0. The second rule, the derivative of a polynomial term, and that's always going to use that shortcut that says take the exponent, bring it down in front, and then reduce the exponent by 1. Then we had the sum rule, which told us how to take derivatives for the sum of two functions. Similarly, the difference rule. Then we had the constant multiple rule. Now, this first rule and that constant multiple rule, they both have the constant c in them, but they're different because this one further down the list is also involving a function of x, where the one at the top is just a constant. And then we learned about the product rule and the quotient rule. The product rule and the quotient rule will be extremely useful throughout the entire semester, and so will the rest of the rules, but these two really save us time when calculating derivatives. The other ones save us a little bit of time, but product and quotient rule, we need those ones memorized for sure. There's a couple of other things that we want to briefly talk about in this section, which is that we can extend some of these rules. For example, the power rule can be extended to work on negative exponents. So if we have x to the nth power, we can also make this work for x to the negative nth power. And the way that I will convince you that this works is to rewrite x to the negative n using a positive exponent. So x to the negative n is the same thing as 1 over x to the n. So I could look at this like I was taking the derivative of that, which we would call a quotient. The top function is a constant, 1. And the bottom function is x to the n. For our quotient rule, we need f prime, which would be 0, and we need g prime, which would be n times x to the n minus 1. And applying the quotient rule, we have f prime times g minus f times g prime, all divided by g squared. Now in our numerator, 0 times x to the n, that whole first term is gone. So really what we have is negative n x to the n minus 1 over x to the 2n. And if we use our exponent rules again, we can rewrite this as negative n times x. Notice that we have x as the base for both of the factors in the numerator and the denominator. So we can write the exponent from the numerator, n minus 1, subtract the exponent from the denominator. And then we simplify that. Combining our like terms, we get negative n minus 1. And this looks a whole heck of a lot like the rule for x to the n. So remember, if we were looking at the derivative of x to the nth power, we said just bring down that exponent, multiply it in front, and then reduce the exponent by 1. That rule was assuming n was positive. We just went through the case where n was negative, and we're noticing the same pattern. So that power rule works on positive and negative numbers, not just positive numbers. And then over here on the right, we can extend the power rule for rational exponents, so fractions, which is really nice. And we can do this very similar to the way that we did the extension of the negative exponents, so I would challenge you to try this one on your own. Another rule that we can extend is the product rule. I showed you the product rule when we had two functions multiplied together to create that j function. But what if we had a product of even more than two functions? Maybe, say, 3 functions. Well, the pattern continues. We're not going to go through the entire derivation of this, but I will show you that the pattern continues. You need the derivative of each function times the other guys. So notice that in each one of these terms, only one function has its derivative taken, and it's being multiplied by the other 2 functions. And then we're adding all 3 of these together. So if you have 3 functions multiplied together, you'll have 3 terms. Each one of those terms will have one derivative in it. If you had like 7 functions multiplied together, you'd have 7 terms, and in each one of those terms, one of the functions would have its derivative taken. One of the most useful things of derivatives is being able to find where a tangent line is horizontal. Where does the rate of change go to 0? So if we wanted to find that, we could quickly calculate the derivative now, rather than finding the derivative using the limit. So I'm going to take the derivative of this f of x function. which has some polynomial terms added and subtracted together and a few constant multiples on some of those terms. So x cubed becomes 3x squared after taking the derivative. Negative 7x squared would become 7 times 2x. 8x just becomes 8. And then 1, since that's a constant with no variable factors, that would go to 0 after taking the derivative. So again, we quickly calculate f prime. We find it's equal to 3x squared minus 14x plus 8. And if we want to know where is the tangent line horizontal, that's the same thing as asking where is your derivative equal to 0. So we will calculate the derivative, then set it equal to 0. F prime for this problem was 3x squared minus 14x plus 8, and if we set that equal to 0, that will allow us to find the x value that forces the derivative to be equal to 0. So solving this equation for x, we can find the x value that forces the derivative to be 0. To solve this, we could use the quadratic formula. We could factor. There's lots of different ways to solve quadratics. I'm going to go ahead and use the quadratic formula. X will be equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. And then we'll clean this up. So then x is either equal to 14 plus 10 over 6, or x is equal to 14 minus 10 over 6. So we get our two answers here. 24 over 6, that simplifies to be 4. And 4 over 6, that actually doesn't simplify to be a whole number, but we can reduce that fraction to 2/3. So what we just found is that for the function we're looking at, it will have a horizontal tangent line when x equals 4 or when x equals 2/3. And we can test that. If we plug 4 into the derivative, we get 3 times 4 squared minus 14 times 4 plus 8. And if we type that into our calculator, we get 0. And same if we had plugged in 2/3. Type that into our calculator, we should get 0 here as well. We will definitely do more of this throughout the semester, but this is just a taste for how much nicer these application problems can be now that we know how to calculate a derivative without a limit.